Right. Emoji wise, how are we doing? So hi. Who else? I use this to get a gut feel for how things are going. So that would be a far more typical response, Michael. I think 3 days into C programming is probably pretty usual. I was about to say something about it's like being on a boat. After a while, you don't puke anymore, and then, but I that started to turn into like a pun about seasickness, and I shudder to even say that. Let's see here. Who else? I know there are more than two emojis out there. So here's the thing about C. It's so different than what you know already, and it requires so much hand holding that it can be difficult to figure out exactly what it wants out of you. And that can definitely be frustrating. But that said, I can assure you that after a while, you get used to these little things, and then C programming becomes much easier and just gets easier and easier over time. And it's like this basically with every language you learn. And some of them are more quirky than others, but it's going to be unlikely that in your career you make a larger jump than you just have made from Python to C. Pretty much every jump you'll make in your career will be easier than this. So there's that to look forward to. And I'm confident you can make the jump anyway. It's just the first few days are going to be frustrating. When I learned C, the first few days were frustrating. When I first learned pointers, well, to be honest, I mean, doing things with pointers the way we've been doing it, that was something you kind of mess with and you're like, okay, I sort of see how this goes. You see that after a week or so, but it took me like a couple of months before I was super comfortable with just doing pointer stuff whenever. So again, I just like to stress that if it's not coming to you immediately, that's okay. This is the way it goes for everybody. So while it could be frustrating, don't let it be worrying. You can figure it out. Oh, all the puns. There was a really good book uh, by Peter Vanderlinden, I think was his name, uh, called Deep Sea Secrets. It was the only other C book I ever owned. But he has some good stuff in there, kind of intermediate level stuff that you learn to get up to intermediate level. Oh, all right. So yeah, for this Q&A bit, I'm just going to hack on stuff that you guys want, that you have questions about, so we can use this as more of a solutiony type thing. But you have to ask, because I don't want to do the whole thing as a solution because that'll take too long. So it'll be more directed here. But so far we've had memcopy and memory size with casting and free. So we can totally talk about these things. Let's see. Let me close that up and open one of these. I've just cloned this repo fresh, so define string. I'll do quick sort if I have time for it. All right. Let's do some memcopy stuff. So memcopy receives a block of memory of any type, copies its contents to the destination pointer, and is the number of bytes to copy. You might remember from yesterday we had a couple options when we were copying things with pointers. We could either look for some kind of terminator at the end, like the null terminator on a string, or the example we used yesterday of a terminator of 9999 on a list of integers. You could do that, or you can pass in a length, a number of bytes, or a number of items to process. So we're going to, in memcopy, we're passing in a length, the number of bytes we want to process. I want to share my screen. Man, is it going to be one of those weeks? All right. So what do we have? Destination, source, and end. This is exactly the function signature for the built-in memcopy function that we'll be implementing ourselves. So here we're taking advantage of something kind of interesting. It says it copies or receives a block of memory of any type, and it copies the contents to the destination pointer. That's kind of what the void means right here. So void pointers are pointers to memory. And remember, a pointer to memory is just an index into memory. So void pointers are numbers that are indexes into the memory array. They just don't have a type associated with them. So if you were eagle-eyed over the last couple of days, you might have noticed that unsigned chars or chars take up 1 byte, but ints might take up 4 bytes. And an array of ints might take up a whole bunch of bytes. So the size, or a struct is another example. A struct takes multiple bytes to store all that information. So a void pointer can point to any one of these types. It's just that we can't do anything with it because there's no size or type associated with it. So we can't dereference a void pointer because it's a pointer to what is the question the compiler has. Like if it's a pointer to an int, I know I can give you an int if you dereference it. But if it's a pointer to a void, I don't know what to give you. So we have to convert that void pointer into a specific type of pointer, and then the compiler can dereference it. So let's do that first of all. One more thing I want to say is that another feature of C is that you can take any object that you have in memory, whether it's an array or an integer or a struct or anything, and you can copy that object by copying the individual bytes of it. So we're going to take advantage of that, and we're going to copy 1 byte at a time from the source to the destination until we get up to the number of bytes to copy. So there's a hint here. Number of bytes to copy. You may want to cast the input pointers to char pointers first before performing the copy. So let's do that first. I'm going to make source. I'm going to call it S, and I'm just going to do this. And I'm going to do the same thing here with destination. One of the features of void pointers is that you can convert them to any other pointer type without a problem. So here I'm basically saying, hey, S points to the same thing that source points at, and D points at the same thing that destination points at. The only difference is that source and dest are void pointers, and S and D are char pointers. Now, sometimes you'll see people explicitly cast like this. When you put parentheses and a type in front of an expression like this, it says, hey, whatever that was, force it to be this. But it turns out in C, casting explicitly like this is very rarely actually necessary. And so I'm just going to take advantage of the fact that that in C we can automatically convert from void pointer to anything else. Let's see, source cast, char source versus char pointer source. Oh no, sorry, I'm missing the pointers because they got the asterisk got erased, but I see them. Let's see, char pointer source cast equals char pointer source versus, yeah, that. No, you don't need to do the explicit casting. I I seem to remember off the top of my head that there are like two places that you absolutely have to cast in C to get rid of warnings, and I can't remember what those two places are. Anyway, so I've got source and destination, and I want to copy n bytes. There are a whole bunch of different ways to do this. We can use for loops, we can use array notation, we can use a while loop, we can use pointer arithmetic, because pointers and arrays and pointer arithmetic and arrays are basically the same thing. But if I want to, again, we can approach it this way. If I want to copy the first byte, I could just do this. I could say, take whatever is at the destination. So D is a pointer to a byte that we want to copy, and I want to know what that byte is. So I dereference it to get what that byte is. I will say, store that thing at whatever is at the source pointer. So this is copying the first byte. Take whatever's at the whatever the D pointer is pointing at, and store it at whatever the S pointer is pointing at. And we could do more of these. I copy the second byte, and so on. And the third byte. And here we're using pointer arithmetic. And of course, now is where we're thinking that we might want to do a loop. And we know how many bytes we want to copy. We want to copy n bytes. We pass that in. So we could do something like this. There are a lot of different solutions here. I'll use pointer arithmetic-ish solutions. So I0, I is less than n, I plus plus. Actually, no, let's just use this. Let's just use array notation first, and then we'll do a pointer arithmetic way. I wanted to take whatever is at the destination, and I want to store that whatever is the source. Nope, wrong way around. Source, destination. Let's do it the right way around. Destination equals source. Yeah, sigh. Yeah, it's backwards day. All C programming is backwards today. That's my excuse. What happens if dest is pointing to something not a char? That's a great question, because here we are, we're just copying individual bytes. So this ties back into the fact that even if it's pointing at something else, we can always copy that thing by copying the individual bytes of that thing. So I'll do an example in a minute where we'll pass in a different thing to copy. That's not chars at all. And what our code will do is go one byte at a time and take whatever that thing was, and our code doesn't care, right? Memcopy doesn't care what the thing was. All memcopy cares about is it's made up of bytes, and all things are made up of bytes, and we're just going to copy those individual bytes of that thing. So let's see, and then we want to return something. This doesn't say what we want to return, does it? So this would be a great place to ask me, the client, a question. The function signature said we should return void pointer, but the description doesn't say what we should return. So in real life, when you find something like this, figure out whoever wrote the specification and say, hey, what about this? Because that's a great question to have. With the real mem copy built in, this returns a copy of the destination, just for convenience. Sometimes the caller wants to get it back as a return value, but usually it's just ignored. But we want to return a copy of the destination, and destination is a pointer, so we want to return that pointer. This is the whole return type right here, void pointer. So I'm going to return the destination, which we haven't modified at all. So I think that should work. I'm going to write another variant of this code right here. So let's do it a pointer arithmetic-y way instead of an array notation way. Of course, with array notation and pointer arithmetic being the same, we could always rewrite this as dereference d plus I and dereference s plus I. I'd say that's kind of rare though. If C programmers find themselves writing these lines like this, they usually just replace it with array notation like that because it's more concise and they know that they're equivalent. But we could write code like this. Let's see. Let's do something completely different. I might have an off by one error here. What about that? Should be greater than or equal to 0. Let's see. 1 byte, 1, 0 bytes. No, it should be greater than. Okay. So we've got a for loop here that works. Here's a while loop that does something very similar. Except pointer arithmetic-y. So n starts at some number like 10. We copy a byte. We increment the destination. We increment the source pointers. And then we subtract 1 from n. And when n gets to 0, we stop. So hardcore C developers might even try to go more compact using post-decrement. Things like this. I'm not sure if this one works. We might have to give it a try. But these are kind of the two main solutions here. An array solution and a pointer arithmetic-y solution. You could have also written this as a for loop. Like this line could have been written with no initializer while n is greater than 0. We could have written it like this too. Let's see, that moves all this up. Let's see, we should see if we can make this run. Let me see here. Yeah, it's not something, Jonathan, that point, it's not something that's naturally occurs to people because these variables seem kind of special, right? Because they're up here in the function signature. But it turns out in C and in JavaScript, for that matter, and probably in most languages, these are just local variables. It's almost exactly as if you had just declared them in here. They behave the same as local variables. The only difference is, of course, they get copies of whatever arguments you called the function with. So n gets automatically initialized to whatever you called the function with. But Aside from that, it's just a regular local variable. Let me see here. I'm going to copy this. Let's see if I can get this to go in Python tutor here. See if we can mem copy some things. And I'll bring the screen up for you guys. Okay, so this char buff 100, we're going to mem copy a thing. It's destination, source, and number of bytes. I'll copy 6 to include the null terminator in there. All right, I feel like I've done something wrong, but I'm not sure what it is yet. Ah, interesting, Jonathan. Yeah, there's something maybe similar in Rust where you can't actually change any variables. Charcoal S, hello, get my variable names right. You can't actually change any variables unless you specifically declare them to be mutable. All right, what do we have here? S is a pointer to nothing. Let's step forward. So we go into memcopy. We've got, because that is 100 bytes, it goes way out to there. That's not nice, is it? Let's make this something more reasonable. Yes, Carlos, that's exactly right. If you only memcopy part of the string, you won't get the null terminator. There's another function built in called strcopy that's specifically for copying strings, that is, arrays that have a null terminator at the end. And that will copy the null terminator, but memcopy is just straight up bytes. It doesn't care if it's a string or whatever it is. So here I'm going to copy a string. There we go. That looks a little bit better. All right. Dest source. Why is my S pointing to nothing? I feel like I broke the visualizer. It says source is pointing to nothing, so S is pointing to nothing, but it's clearly copying. Pointer S equals hello, buff S. Oh, it's because my local S is hiding it, probably. No, that can't be it. You guys see that I'm doing anything particularly dumb here that's causing the visualizer to not work? Let me get rid of the const. Yeah, that'll be the case when n is down to 1. Well, geez, guys, how am I going to demonstrate this if my S pointer is all busted? Well, at least we see the copy happening. There's our null terminator, and we're done, and we return dest. I don't know why it doesn't know what S is. It thinks S is a garbage pointer. I'm going to change the variable names and see if that makes the visualizer happier. But then also we'll just try copying some different stuff that's not a string. Let's also switch to our other for loop. And see if this one works just as well. All right, hello, and this. Nope, still gets trashed. That is so peculiar. So here I'm stepping through. We see the source and destination pointers. At least this time we see it consuming the hello. And the null terminator. And then we're done. So it's working, even if the visualizer isn't working. But let's copy a thing that's not a string. I'm going to make something up entirely different. I'm going to make a struct foo type. It's going to have an int x and a float y in it. So something that's not the char array at all. And I'm going to make two of them, A and B. And I'm going to say A.x is 10 and A.y is 3.14. All right, so I've initialized A, but what I'd really like to do is copy it into B. So let's look at this first. I can put size of struct foo here if I want, or I could actually just put size of A. Or yeah, I can just put size of A here, which will give me the number of bytes that this is. And I want to copy one of them. That's how many bytes I want it to be. But there is something wrong with this code. Can anybody see what it is? It has to do with the types that that memcopy is expecting and the types that I gave it. So I'm calling it like this, and the signature looks like that. So the address of, so what type, what is the type of A? Remember we were doing that type exercise yesterday? What type is A? Anybody? That's not how I have it declared. It's of type struct foo. Because I declared it right here. A is a struct foo. FTW for the win. And that's fine, except that memcopy expects a pointer to a void. Remember, pointer to void is pointer to anything. So pointer to void is the same as pointer to struct foo. So what I'd really like to pass in is a pointer to a struct foo, but I'm not. I'm passing a struct foo. So I need address of I need to take this guy and turn it into a pointer to that thing, and this guy and turn it into a pointer to that thing, and that'll make it work. So let me get rid of my scratch paper here and pop down to the bottom of the code, and I'll say I want a pointer to A and a pointer to B, and then I want to memcopy those things. So let's give this one a shot. I'm going to put in an extra line here that does nothing, just to make sure that I have a spot to see the variables at when we finish execution. Okay, so let's step through here. So A.x is 10, A.y is 3.14, B is nothing. We're going to jump into memcopy here, and I've got my source and destination pointers. And you see it's pointing at A and B, which is great. And then S and D are also pointed in there. That's a lot of lines. Wonder how this is going to visualize. Now we're going to go through a byte at a time. It says N is 8, so that's how big our structure is, 8 bytes. And so we're going to copy things one at a time, and I'm hoping that, there we go. So after the first 4 bytes were copied, we see B.x is now 10, because integers are 4 bytes. So it took 4 bytes to copy that over to 10. We'll step through the last 4 bytes, and now we have 3.14 in there. And then we'll return our dest, which we're ignoring. And here we are. Now we see in B, we've got 10, 3.14. It's made the copy successfully. Just doing it a byte at a time instead of the whole structure at a time. There we go. So not only does it work on strings, but it works on arbitrary structures. We work on arrays of structures too. You just have to pass in the correct number of bytes to copy. That's really the trick. You can pass in pointers to whatever you want, but N has to be the right number of bytes to copy. If we did something like this, let's purposefully break this. So instead of copying the whole structure, let's copy the structure, but then stop 1 byte short and see what happens. So this is wrong because we want to copy the whole structure normally. But if we stop a byte short, let's see here. I'm going to skip ahead in execution. So there we are. We've stopped a byte short. We jump out here to the end. It's the visualizer just telling us, so I don't know what's in there. So it didn't make a full copy. It copied all the bytes but 1, and the last one was left off, which means it was a corrupted copy and didn't happen fully. But as long as you know the correct number of bytes, what happened? The correct number of bytes, then you're good. Questions or thoughts? When do we need to create malloc when initializing a new string or array variable? So let me answer this in a couple ways. Firstly, there are kind of 2 ways to allocate space for a thing. One of those ways is what I'll call the normal way, when you just declare something like this, int n. We've allocated space here for an int, which is fine. We didn't have to malloc anything. We have space for it. We stored a number in it. This is like what you're normally used to, right? So that's one way. The other way is to malloc stuff. And this this gives you some memory elsewhere on an area that we call the heap. So int n here on line 74, this would be stored on what we call the stack, and target, the space for target here from this malloc, this is stored in what's called the heap. Stuff that's on the stack, like this int n, they are impermanent. This int only lasts as long as the function, because it's a local variable, right? You're used to that behavior as well. You have a local variable. Once the function returns, the local variable is gone. But stuff that you malloc, this stuff sticks around for as long as the program runs or until you free it. And that goes on the heap. So the question is, do you want stuff on the stack or do you want stuff on the heap? Putting stuff on the stack like this is often easier. So this is the way people prefer to do it. That said, sometimes you want some memory to persist between function calls. You want it to persist longer than one function. Once the function returns, you still want that thing out there. And if you still want that memory out there on the heap after the function returns, then you have to malloc the space for it. Yes, it definitely can be. That said, usually it's not used with global variables. Usually local variables are passed around that are pointers to that thing. So in this example here, line 75, we've allocated some space on the heap that's out there somewhere. And then we have a local variable called target that points at that stuff. So even though the space is out there somewhere on the heap, target itself is a local variable that we have. And once this function exits, target will be gone. So if you wanted to use it elsewhere, you'd have to pass a copy of that pointer to another function so that that other function could use the space that was on the heap. So it can be used with globals, but often we just use it with locals, just like we've done here, where target is a local variable. And then like here, target's a local variable. We call memcopy. It takes the local variable target and it copies it into this local variable dest, right? So now in memcopy, dest also points to that malloc space. I don't know if is that useful? Malloc, you can think of it as like, hey, I got a block of memory that I just allocated somewhere, and here I've got a pointer to it, but I can pass copies of that pointer just to other functions. And so other functions could have pointers that all point to that one block that we've malloced. So the stack doesn't have what we call a garbage collector as such. The stack merely frees all its local variables when you return from the function, and that's pretty unconditional. So when you have local variables in your function, when you call the function, space on the stack gets allocated for it, local variables go in there, and when you return from the function, all that space just goes and vanishes. So it's not really garbage collection. It's just like, oh, hey, for this function, I need 400 bytes for local variables. So bam, there's 400 bytes in the stack. We'll use those. Function returns, bam, stack's back to normal. It's gone. But malloc persists through functions because it's out on the heap. So if you're running your function, bam, you get space for local variables. You run some code that mallocs something, that allocates a chunk way out somewhere else. And then when the function returns, the stack is reduced again, but that thing that you malloced, that's still out there, it's just hanging out. So it's important when you malloc a thing that you always have a pointer to it somehow. If you lose all your pointers to the thing that you mallocked, you can't free it anymore. The memory is permanently lost, or permanently throughout the run, I should say. Once the program exits, all the memory gets freed. So why didn't C create a garbage collector for the heap? My best answer for that is that is un-C-like. That it goes against the theme of the language. A garbage collector is kind of a heavy-handed and complicated thing. And the main complaint against garbage collectors is you don't know when they're going to run. So what garbage collectors do is they run through the heap and they look for things that nobody's using anymore. And if you're not using it anymore, it automatically frees it. And it's really great from a programmer perspective. When you're programming in JavaScript or whatever, you don't have to think about freeing memory ever. You just make copies of stuff, and when you're done with it, you just ignore it. And later on, the garbage collector is like, oh, hey, nobody's using this object, so I'm going to free it. It's really convenient, but the garbage collector is complicated, and it takes time to run. And people who program stuff in C, they're often programming embedded systems like anti-lock brake controllers, stuff like that, where timing is really important. And you don't want your anti-lock brake controller to be like, oh, hang on a second, I got to do garbage collection. Just hold on. It won't be long, just half a second. Like that could be a big deal when you're in an emergency braking situation. So when we use malloc, we got to use free when you're done with it. Yep, that is the rule. If you malloc a thing, you should free that thing sometime. If you malloc stuff and don't free it, we call that a memory leak. And in programs that run for a long time, say like a printer driver that's sitting in and just running forever, or a print spooler, I should say. If that thing has a memory leak and it leaks like 2 kilobytes of memory per day, after it runs for a year, you're like, where is all my memory gone? The Rust programming language uses an interesting and complicated programming mechanism to make it feel like a garbage collected language without using a garbage collector. Anyhow, let's jump into this memory resize thing. See how this goes. Give it a pointer that malloc memory. This function will attempt to resize the allocated memory to a new specified size. Any data that was previously in the old malloc memory should be intact in the new resized block of memory. So do not use the realloc function from the standard library. This is, in fact, what realloc does. If you've malloc some memory, let's see, where's an example? When you malloc memory, you give it the number of bytes that you want to malloc, right? So here we've said we want to take the number of bytes that an integer is and multiply that by n, and we want to malloc that many bytes. And this is just a way of saying we'd like to allocate space for n integers, please. So if we've allocated space for that and we've put stuff in that memory and we want to change the size of that memory, that is, if we allocated space for 10 ints, maybe we'll want to change it to now be sized for 20 ints. What do we have to do to make that happen? What do we have to do to make that happen? And then after we resize it, we want whatever data was in there, we want that data to still be in there. So, let's see if we can make this thing up. We have a pointer to the data. We have how big the old data was, and we have how big we want it to be afterwards. And then we return a pointer to the new thing. Size memory, new length, blah, 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 well, path. All right. So first of all, let's get space for the new size. So I'm going to call this, I can use void pointers, I think. We'll find out in a minute. So I'm going to call this destination, or what should I call this? The new space. The new space. Let's allocate space for it. So we know that at the end of this, we want the new memory space to be new size big. So I'll just make one of those to start. And then we want to, and I'm going to want to return that, I guess. So let's return it. So that's great. But of course, what makes resize memory special is that we copy the data that was here into the new space before we return. I see typing. So let's see, I couldn't find use for both old size and new size in this function. Well, we will find use. Namely, we know that the data that was there is old size bytes long. And so when we copy the old data into the new space, we want to copy old size bytes, maybe. And new size we got to use to allocate the new space. But why void pointer? Uh, this is because I'm not sure what type I would want it to be. So Malloc returns a void pointer. So new space is a pointer to a void. I'm just not sure what I'm copying yet. And I'm guessing, peering ahead, I'm guessing that I actually don't care. Because we don't know what type it is. Yes, exactly. But what I do know, there are two cases here. It points them out here. Uh, old size could be less than the new size. It could be greater than the new size. Let's take these cases one at a time. Let's assume that the new size is bigger than the old size. So before we had like 5 bytes allocated, let's say the new size is more than 5. So we know that all the data that was there can fit in the new space. So we don't have to worry, let's not worry about the case up front where the data that was there won't fit in the new space. Let's just copy that stuff over. So how do I copy old size bytes from pointer into the new space? Ideas? Similar to our last function. In fact, very, very similar to our last function. It's so similar, in fact, that I think I'm just going to use our function. I want to copy memory. I want to copy old size bytes of memory from pointer into new space. Let's just do that. Let's see, destination is new space. Source is pointer, and the number of bytes to copy is old size. And since memcopy takes void pointers as arguments, I have no problem here. I don't even have to change this to anything else. And I think this should work for the case where new size is greater than old size. Unless I'm missing something obvious here. What happens when new size is smaller? That's a great question. Because what are we saying here? Let's say old size is 10, new size is 5. So I allocate myself 5 bytes right here. And then I say copy 10 bytes into it. Guesses? What do you guys think is going to happen when we copy 10 bytes into a 5-byte space? These are good guesses. Uh, Cameron, only the first five get copied. I would say, yeah, but our code clearly doesn't do that. Our code doesn't stop. It'll copy the first five, but then it's like, I'm going. You told me to copy 10, so I'm copying 10. So you'll do whatever you ask, even if you ask it to drive over a cliff. So Steven has it right. Undefined behavior. Uh, so with undefined behavior, Cameron, I'm going to back up and say it's possible only the first five get copied. Because when undefined behavior occurs, anything is possible at that point. Probably a crash, maybe not a crash, maybe it works just fine. It's undefined. So that's one of the undefined behavior rules in C. You can Google if you're curious what causes undefined behavior in C. But one of them is accessing memory space that you have not allocated. So so we better take this into account. What can we do? It seems like if the new space is smaller, then we only want to copy the smaller size, right? Throw an error. See, this is a good question. It doesn't actually specify in the spec here what to do. What do you do? So we could throw an error. We could totally do that. A common way to do that would be something like this. If new size is less than old size, then return null. When a function returns a pointer of any type, returning null is often the way the errors are indicated. So we could do that. But it would be a good question for the spec writers. What do you do? But yeah, and your other point there, Stephen, that like doesn't seem like useful copy function. You just throw out half your data and have the program not bat an eye. Maybe that's true, or maybe that's the behavior that's desired. It wasn't clear in the specification, so it would be something to clarify. And when you guys are at work, you're going to find specifications all the time that are unclear. So, but we could do this. This is an option, like just return an error. I don't think that's what the test wants, though. Psi has another idea. Use the minimum of these things. So we could have something like this. Bytes to copy, and if let's see, if the new size is less than the old size, then bytes to copy is the new size. Otherwise, it's the old size. There are several different ways to write this as well. And then we change this to bytes to copy. Did I do that right? So it'll take the smaller of the two of them. Some people might write this with the ternary operator. I don't know if you guys use the ternary operator very much, but this line is basically equivalent to these lines here. Does Swift have this operator? The question mark colon. It's such a cool thing. All languages should have it. Rust does not have it, irksomely. So if we do it this way, then I think this is close to the solution, if not the solution. Uh, Allocate some space, figure out how many bytes to copy. We copy either the old size bytes or the new size bytes, depending on which one's smaller. We copy that into the new space, and then uh, we return. There are some more corner cases we haven't taken into account here. I'm not sure if the testing looks at them or not. Like the user might pass in new size as 0 or some negative number, or old size as 0 or some negative number. Why they would do that makes no sense, but they might. Maybe you want to handle that case. So were there other implementations that any of you used for this? Yeah, Cameron, what if new size equals 0? It would, actually, I don't even know. What happens? Look up the man page for Malloc right here. Let's see. Malloc, allocate size, reallocate. I don't actually know. The man page for Malloc isn't elaborating what happens when you pass in a size of 0. All right, here we go. The result of calling malloc 0 to allocate 0 bytes is implementation defined, which means it's not undefined behavior. It means that it could be different on every system. So, oh, we could totally do that, Cameron. Like maybe if the new size is 0, they wanted things to deallocate. Maybe they wanted like, oh, hey, we're done with that thing. Or something. Oops, return null, yeah. Oh, what happens to old space? Yeah. See, I totally broke the rule. I have to free it. I knew I was forgetting something in all this. After we mem copy it, let's get rid of it. Holy cow. See, I had a memory leak right there. Andrew, Carlos, good eye. That old memory space would have just been floating around forever. I repeated myself on line 63 and line 79 here. I could probably refactor that to not do it, but so free deallocates the memory that you allocated with malloc. So when you malloc a thing, that chunk of memory sits around forever until you free it. That's a great question, Jonathan. Miles, the malloc is implicitly called in parameters. The parameters, since they're local variables, those all exist on the stack, so they don't have to get mallocked. The compiler makes sure there's space on the stack for those variables, but it does that implicitly. Um, I'm not aware of any operation in C that implicitly does a malloc. Yeah, in this case, for resize memory, we are assuming that pointer was something that we called malloc on. So if I pop down here to our call, we see that URL is the pointer, and URL is not a pointer, or URL is not. Oh, it is malloc. It's hidden away. Stirdup. Stirdup has a malloc in it. So this is one of those cases where it doesn't look like we're mallocing it, but Stirdup has a malloc in it, so it is actually malloc. If you try to free a pointer that you didn't malloc, it's gonna, bad things will happen. Let's try a quick test. I'm just going to write a short program that has an int a, which is 12, and an int pointer p, which points to a, and then we're going to try to free it and see what happens. So I'm freeing a pointer here to a thing that I didn't malloc. A is on the stack, not on the heap. So, oops, lib. Is that where free is? I can't remember. Blah. Error for object this, pointer being freed was not allocated. So here I am trying to free something that I did not malloc, and it pukes. But if I were to malloc this thing, we'll allocate space for one integer there, and then we'll set it to 12. Now it should be happy because we're mallocing something and freeing it, and it's no problem. Let's see, how long does the memory leak persist? It persists as long as the program runs. So when the program exits, then all memory and all resources associated with that program are freed up. So it's not like you lose it forever. But if you have, like I said, a long running program that's expected to run for as long as the computer is up, and there are a lot of programs like that, if they have a memory leak in there that leaks memory over time, you'll see that slowly consume all the memory on your system until that program exits when you reboot. Oh, I'm not aware of any. Or at least any that leak memory badly. It's a common defect. So I'm probably running programs on my Mac right now that came with it that have memory leaks in them. That said, modern programming languages work really hard to prevent these. In Rust, you can't have memory leaks unless you're really unless you really work hard to make it happen. You have to go out of your way. Swift, it's probably really difficult to leak memory. JavaScript has a garbage collector, so it doesn't leak memory. But C doesn't have any of that stuff, so it's more than happy to, well, you allocated stuff, but you never freed it, and you know what? I don't care. C's offhanded that way. Cool. Let's take a break because it's been a long time. Let's take a 5-minute break and grab some coffee and hack on more stuff. Why doesn't the non-pointer variable need malloc? Because it's on the stack. So that's the, remember there are 2 places you can store stuff, on the stack and on the heap. All local variables get stored on the stack. So the C compiler, when it generates code, it automatically allocates and deallocates that space as you do stuff. So if I call a function here like foo, do something like this. What we have here is a bunch of stuff. We have a number of local variables. We got local variable p, that's on the stack. It'll go away automatically when main returns. But the stuff we malloced, that's on the heap. That memory doesn't go away. Over here in foo, we've got int pointer x, that's a local variable in the stack. Int a, that's a local variable in the stack. X points at that memory that we malloc that's way out there. I'm dying to run this through the visualizer. But let's take a break first. Grab that coffee and we'll come back in 5. I'll start a timer up here somehow. Let's see, not like that. What am I doing? All right, catch you guys in a few. right, gang. Hope you got something warm to drink. You really want me to get rid of the rooster? Fine, I'll get rid of the rooster. Hmm. There's a line from the movie The Big Short, which is a great movie if you haven't seen it. But the guy was saying, yeah, it was like, my wife tells me I'm unhappy, and his business partner says, but you're happy when you're unhappy. I was like, I am happy when I'm unhappy. Oh man. Okay, I want to demonstrate this little thing really fast because I was dying to run this through the visualizer to see what happened, because it does stack and heap stuff. So here we have the stack that shows all our local variables in a function. So we have our main function, local variable p, right there. And then we've got the stuff that we've allocated on the heap, which is currently nothing. But if we step forward over this line, we see we've allocated space for one integer on the heap. And there it is. It's calling it an array of one element, but that's fine. It's space for one integer, and p points at it. That's the line of code we just executed. P is a local variable to main, so it'll be gone when main finishes. But let's continue forward. We assign whatever p is pointing at, we assign it to 12. So p was pointing at this thing on the heap, so we put a 12 there. Perfect. And then I'm going to call foo and pass the pointer p in there. Now, foo has a local variable x in it. That's going to get a copy of p, because that's what happens when you call functions. You get a copy of whatever argument you passed in. So remember, p is pointing at this thing, but p is not this thing. The actual value 12 is out there in the heap somewhere. It's its own thing. P merely points at it. So when we call foo, x gets to be a copy of p. So now both x and p both point at that thing out there that's got a number 12 stored in it. And then I've also got a local variable a here in foo. So both x and a are local variables. They're on the stack. They're going to be deallocated automatically when the function exits. So here we set a to 55. And then I say whatever x is pointing at, set its value to a. So this will set whatever x is pointing at to 55, and we see it change right here. Notice that both p and x are still pointing at this thing out on the heap. So the value of dereference p down here in main is now also 55, because they're both pointing at the same object. We come back to main, all our local variables from foo, they're all gone. The code automatically deallocated all that stuff because it was on the stack. But we still have our pointer p pointing at the 55, like foo changed it, until this line, when we free it up, and now p points at garbage, and then we return and the local variables are gone. So I hope that was kind of a useful demo-ish. Yeah? No? What I really like about it is that we see the thing on the heap, and we see the two pointers pointing at it at the same time. P back from main and from x from foo. Thumbs up, thumbs down. Cool. This also kind of shows that even though p is a pointer, it's just a regular local variable. Even though x is a pointer, it's just a regular local variable stored in the stack. It's just, instead of storing a thing like an int, it stores a pointer. So, cool. Let's see. So when creating an instance of struct, we need to declare memory size for creating the malloc. Suppose we have a struct that includes a string of undeclared size. Let me code that up in a big hurry because this is a fun question. Let's see here. So let's say we have our favorite struct animal, and inside here we have a name for the animal, and we also have something else like leg count. So I've got that, and let's say I want to dynamically allocate one of these. A common thing to do would be to write a function, it's called animal new, something like this, that takes a pointer to a name and a leg count, and you pass this stuff in, and this thing would be like a constructor, basically. And then we're going to return some new animal. So this constructor needs to do a couple things. It needs to allocate space for that animal, and then it needs to return a pointer to that animal. So, oops, struct. I'm going to go ahead and allocate space for it. So I'm making space for one animal. I'm going to return that at the end of the day, because our return type here is struct animal pointer. And then we're going to initialize it. Now remember, with regular structs, you use dot notation to initialize. But since this is a pointer to a struct, we use the arrow notation. So this is going to equal something, and leg count is going to equal the leg count we passed in. So this is kind of the crux of the question, right, Si? Like, what do we do with this char pointer? So I'm going to demonstrate a couple things here. One of them is what it means to be a string in double quotes in C. So we could actually do code like this. And name equals name, and then we could do something like this: struct animal pointer my animal, or let's make it real. Let's make it a real animal. My favorite animal, a new goat with 4 legs. So this is actually legit right here. This will work. It turns out if you have a constant string in double quotes like this, this pointer is good for the life of the program anywhere. It's effectively global. So we could have a constant string like this. We could store the constant string like this. Both of them will point at the string goat. And everything will be good. Should I see if we can, let's see if we can put this into the visualizer or not. Assuming I haven't made horrible typos. All right, let's see what happens when we run this. So I'm going to step into new goat. So goat's a pointer in main, doesn't point to anything yet. Here we are. I've got a struct animal. Okay, name points at goat, so there's our global goat name. That's fine. I've allocated space. I copy the name pointer. So the name that we passed in points to that constant string goat. Also now the name in the new struct animal points to it. And leg count gets set to 4. And then we return that animal. And there we are. Now goat points at this whole struct animal. The name points at the constant string goat that we passed in. So that kind of worked. But what if goat isn't a constant string? What if it's something that was declared on the stack somewhere and we wanted to make our own copy of it? So, like, let's say we didn't want to have a copy of the pointer, but we wanted to actually have a full copy of that string. That is, over here when we were running, let me step back, we have one copy of the string in memory at all, and both of these pointers are pointing at it, maybe it makes sense to make a copy of this string so that we have our own copy. So even if this original one went away for some reason, which it might, depending on how the program is being used, we have our own copy that won't go away. So here's where we want to do something like this. Maybe we want to do a string copy of the old name into the new name. But that's going to crash. Why? Any ideas? When I say stir copy, that's just like mem copy, except it works on a string. So I'm saying take the data that's here, the name that was passed in, goat, and store it at whatever a arrow name is pointing at. So I guess my follow-up question to you is, what is a arrow name pointing at right now? Yeah, it is. A arrow name is a char pointer. That's what type it is. We haven't initialized it to anything though. It's just pointing at garbage right now. So we're saying take the name goat and copy that over there in memory, where over there is some random address that we don't own. We need to initialize a arrow name to something. We need to make space to make a copy into. And so one way we could make space is we could malloc it. A arrow name equals malloc, and then we just need to figure out how many bytes to allocate. We need to know how many bytes long name is. So we can use strlen to give us the length of a string, and that'll help. We actually have an insidious bug right here. Program might run fine, but if the string is goat, the length of goat is 4. But since we know there's a null terminator on the end, we know the actual number of bytes is 5. So even though strlen is telling us 4, we need to have one more for the null terminator. Put my hands on the keyboard in the right place. Maybe I can type here. It's kind of weird. Traditionally, null is spelled with one L when you're talking about that 1 byte null. It's really strange, but there we go. So we add 1 on there. Then we copy the stuff in. And now it should be good. This is kind of weird because first we allocated space for the whole animal. And then once we had it, we then subsequently allocated space for the name. So, oops. Let's copy that and edit this thing. Paste that in here. Let's see how this works now. Oh. Main server is busy retrying with backup server. All right, there we go. So let's see what we got now. So we're going to jump up into our new. We're going to allocate space for our new animal. And then here we're on the line where we're allocating more space for the name. So right now name is pointing at nothing, but after we allocate space for it, we now have another array on the heap here. Check that out. And it just happens to be the exact number of bytes of goat with the null terminator, and we're pointing at it. Now we're going to call strcopy, which is just going to take all the bytes from here, copy them down to here. Then we're going to do our plain assignment for leg count, and then we'll return. So there we are. We've gotten our own copy of the name of the goat, and it's exactly the right length. Oops. But check this out. What happens if we do this? Let's say we did some stuff, and then we free it. Can anybody see anything wrong with what we've done here? This code's going to run fine, mind you. I mean, what could possibly go wrong? Animal new returned us a new animal. That's exactly it, Carlos. We haven't freed the name. We have 2 mallocs, but we only have 1 free. What we really need to do is also free the name that was in there because we had a malloc with it. This is also incorrect, though, because we're not allowed to use a variable after we've freed it. So I have to do this in the reverse order because we can't use goat after we've freed it. So first we free goat name, then we free goat, and then we're done. Oftentimes, because these multiple steps can be hard to remember, because as a programmer, I'm like, hey, I just made a new animal. Why do I have to have 2 frees? Plus now as a programmer, I have to know that name is one of the fields I have to free. Like, I don't want to think about that. I just want to do animal new. So sometimes it's nice to have an animal free function that's helpful to use. And then we do all the dirty work in there that we have to do to free up the animal. And then as a user of the code, all we have to do is this, and we'll be safe. So, and this makes nice code symmetry, right? Animal new, animal free. Oh, let me drop this thing in here. Can you define it inside the struct itself? Yeah, but so I'm going to say the short answer is no. That inside a struct, you only have data, not methods or functions like you do in a class. So that's the short answer. The slightly longer answer after the asterisk is, in C, not only can you have pointers to data, but you can also have pointers to functions. And so what you could do is you could have a pointer to a function inside this if you wanted. It's rarely seen because the syntax is unwieldy, and it's just not very C-like. It's far more C-like to have functions that just take the thing that you want to operate on as the first argument, and that's it. And this takes the place of like self or this. So this is far more common. But you could have, I'm going to digress briefly. No, this is an aside. You don't need to know this stuff. But if we wanted to have something that was like, let's see, animal print leg count, we could have a function like this. We'd still have to pass the animal in. So it just gets so unwieldy. Let me make it not print the leg count. We'll just make a function called hello. It gets so unwieldy that people just don't do this. So I've got this function, and if I wanted that to be a method on animal, I could do something like this. Am I doing this right? If anybody knows the syntax, stop me if I'm doing it wrong. This is just so nuts that now at this point we should be able to do goat.f, and that should print hello. But as you see, that was a pain to set up. Like, not only did I have to use this crazy syntax to declare a pointer to a function called f, I had to declare the function somewhere else. I had to initialize f to point to that function. It was a pain. So people generally do not do that. That said, pointers to functions are awesome. It just has that unwieldy syntax for declaring them. Anyhow, Struct copy, it's CPY. In the good old days, people didn't waste characters like vowels. In fact, there's a system call to create a file, or yeah, create a file in Unix. And you'd think that create is a pretty short word, but nope, they left the E off just to make it that much shorter. Anyway, more questions on this stuff? I wanted to talk a little bit about system calls in the last bit here. I think so. So system calls are like learning how to use the operating system to make it do things. That said, pointers are part of the language, and a lot of syscalls use pointers here and there. So you'll have to know if you're making a certain syscall, like, hey, I have to pass a pointer to a thing. But that's no different than just using regular functions. It's like if you use printf with %s to print out a string, you have to know that the argument better be a char pointer for that, right? Or if you use %d, you have to know that the argument better be an int, that kind of thing. So I think they're easier. Pointers are like a concept, and learning new concepts is hard. But system calls, not really conceptually that different than just calling regular functions. So make it stop. So let me take this opportunity to digress for 5 minutes about what the operating system actually is on your computer. What's everybody running? Macs, PCs, Linux, BSD? Commodore 64s? I see Jeremy's Arch Linux status, so thumbs up there. Are there any BSD users? I don't know. So the operating system does a lot of stuff. But its main job, in my humble opinion, is to protect you, the developer, from the intricacies of the hardware. So we've been using all kinds of stuff while we program, like printf, and we say printf, and some stuff comes out on the screen. And that's awesome. We don't really think much about it. But the screen is a piece of hardware, and there's software that needs to make that hardware go. And we don't even have to think about it. We just type printf, and hooray, we're done. So who's the middleman that's sitting there between our code and hello world appearing on the screen? That is the operating system's, one of the operating system's big jobs, is to protect you from needing to know what the hardware does. If the operating system were not there, you would have to know how to write code to interact with like the video card hardware and stuff, and yeah, it would get bad fast. So in order to be productive at all in this world, the operating system sits there and it abstracts all that stuff away from us. So we can use things like printf and have it appear out on the console, stuff like that. And it's the same with mice and disks and everything. The operating system is working hard with all that hardware to allow you, the programmer, to do things like open a file and read some bytes. When you do that, you, the programmer, you're not worried about like, oh, hey, I've got a hard drive and I need to seek to cylinder 7,900 head 4 and read that block. And you don't think about any of that, right? You just open the file and you read it. The operating system helps that. It also does things like process management. So we're running a bunch of things at once, right? You're watching video, you got the screen share going, you're moving your mouse, you're reading Facebook while I'm talking, all that stuff is happening seemingly at the same time. So the operating system is responsible for managing all these processes. And if I have a look at all the processes that are on my machine right now, clearly I have a whole lot of them going. So the operating system is juggling all this stuff, running all these different things. See if I can get that with more, yeah. Visual Studio Code is running, blah, 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 blah. All these daemons are running in the background. So operating system is juggling all that stuff for me. It's also doing permission things as a user. So it's making sure that if I'm logged in as Beej, I can't accidentally erase the whole hard drive. I have to be super user to erase my whole hard drive, things like that. So the OS is doing a lot of work for us. That said, we can request the operating system do things on our behalf. And when we do that, we do it through functions that we call in C. And these functions that call the operating system are called system calls, or syscalls for short. They look just like normal functions, except some of them happen to be system calls. Let's all go to ring 0. What could possibly go wrong? So we're used to library calls like printf. Printf, well, printf's probably a bad example. Let's use strcpy as an example. Strcpy is a library function that we use, but the operating system doesn't need to be involved. Our program running on its own can just copy bytes. We're good with that. The operating system doesn't have to worry about it. We're not asking it to use a disk. We're not asking it to use the screen. We're just copying bytes. That's it. But if we want to use the screen, if we want to print something out on the screen, or if we want to get something off disk, now we have to ask the operating system to do it for us. Because we, as a normal user, are prevented from doing it. The operating system is like, oh, you want to read the disk block directly? No. You're just a normal user. You can't do that. I mean, it would be carnage if regular users could just read and write arbitrary blocks on the disk. So operating system disallows it. But what it does allow you to do is say, pretty please OS, will you open that file and let me read a block off it? The operating system's like, yeah. Oh, let me check the permissions on the file, make sure you have permission to open it. Yeah, you do. Great. Go ahead and read that block. When we make that system call, we're transitioning into a different mode of execution. Sometimes it's called kernel mode. Sometimes there are different rings, they call them. Or sometimes it's, I don't know, protected execution mode. Have I heard that before? The idea is that when you call the operating system from your program stops running. The operating system takes over to do that work you ask it, and the operating system has permission to do anything. It is like the god of the machine. And so you can ask it to do stuff, and it can decide based on your permissions if it's going to do it or not, and then give you the results back. Your program stops running. The OS does the work, and then starts your program back up again. Remember, the OS is responsible for deciding which program runs next. So after it's done doing the work on your behalf, it can say like, hey, I got that disk block you asked for. Here it is. You can start running again and doing your stuff. So this part for the next couple days, we're going to be messing with the operating system, like asking it to do things for us. And our program will stop running, and the OS will take over, and our program will wake back up again after the OS is done. So what are the system calls? Let me see if I can, we don't need to know all these, but just for the sake of fun, let's see, list of Linux syscalls. See if we can find one. Searchable Linux syscall table, 64-bit. All right, here we go. So not expecting you to know what's on here, but we'll look down the name column just to get an idea of how many syscalls there are. These are all functions you can call that do different things at the operating system level. So there are quite a few of set priority, blah, 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 blah. Look at all this stuff. Lots of things we can do. But let me see if I can get some that are at least roughly familiar. Let's see. Filter. CHDIR. Every process has a current directory that it's running in. You know this because bash is in a current directory, right? You can see what directory you're in when you're in bash, and you can change directories to different directories in bash. When you type cd something in bash, it makes a system call. It makes the CHDIR system call to change directories. If you use fopen to open a file, that's going to use the open system call to open that file. If you use printf to print something on the screen, that's going to use the write system call to print data out to a file descriptor, namely the one associated with the screen. So we have all these system calls deep down, and a lot of the library calls we use actually do call them. Not all of them, but some of them. And we can also call these things directly. There's nothing stopping us from doing that. It's just that things like write is a very simple function. It takes a destination that you want to write to. It takes a buffer, like a pointer to some chars that you want to write, and it takes a number of bytes that you want to write. And that's all it does. It just writes bytes. Printf is really powerful, right? It'll convert a variable into a number. It'll print out floating point numbers. It'll do justification. Printf does a lot of stuff. So it's way more powerful than write, even though deep down it calls write to actually get the job done at the end of the day. But what I want to look at right now is fork. This is my favorite system call. This is how you create a new process in Unix or Unix likes. Let's write up something really fast that creates a new process. For fork, we need the Unix standard.h header file. So this will give us fork. If you ever don't know, you can always bring up the man page for fork, and it'll tell you which header files you need. So, and it'll tell you what the function looks like. It takes no arguments. It returns a type called PID_T, which stands for process ID type. In Unix world, this is an integer type, or a numeric type anyway, but on everything I know it's an integer. So let's make a new process and see what happens. I'm just going to do hello world here, and then return 0. This is normal enough. The fact that fork doesn't take any arguments is kind of weird, right? Let's declare a variable that's PIDT type. I'll call it PID, and then we'll call fork. Doesn't take any arguments, so this is all we can do. Let's print out that PIDT. I know it's, let's see if %d works, or if I get a warning on that. No warning. Let's run it and see what happens. Whoa, that was weird. Let me hit return again. Okay, I'm back out of my prompt. I love it. What the heck happened? We said fork, then we printed hello world, and we printed out the process ID. So we ran it, and the first thing that happened was it printed out hello world and printed 4099 for the process ID. And then I got a prompt from my shell, and then something else printed out hello world 0. What do y'all think happened? Remembering that fork creates a new process. Let's see if we can reverse engineer how all this occurred. Ideas? Or observations? Does the process have to be told to execute? That's a great question. It does not. It simply starts going. Let me do another experiment here. Actually, I'm just going to ignore the return value. I'll just call fork again. Now we're calling fork twice. All right, so if I call fork one time, I get 2 hello worlds. If I call fork twice, I get 4 hello worlds with my prompt stuck in the middle of them. But clearly, if I don't call fork at all, then I'm just going to get 1 hello world, right? Yeah. Yeah, so we actually have kind of 2 things going on here. When I run this, here, let's run it again with the 2. Oops, did that do what I wanted? No, that ran 4. Did I save that file? I did not save the file. There we go. Now this time they appeared without my prompt in the middle of it. That's nice. That time it appeared with my prompt in the middle of it. So what happens when you call fork is it actually creates another process on the spot. So normally when you're running code without this, you can imagine in your head that there's like the process that's running. It's like, okay, I start here, I print hello world, then I return, now I'm done. But if we do this, it makes another process right here. So now there are two. We call them the parent and the child processes. There are two processes running at this point. The parent prints out hello world and then exits, and then the child prints out hello world and then exits. Notice that they print two different things. One of them prints a process ID, and the other one prints 0. So this is a little bit brain bending, which is why I'm stressing it. So when you call fork, two processes exist at this point in the program. They both start executing the subsequent instructions. And the way you can tell them apart is that return value from fork. The parent gets the process ID of the child, and the child gets 0. So this is how you can tell them apart. We could actually write code that looks exactly like this. If PID is 0, I'm the child. Otherwise, get rid of this. I'm ignoring a case where PID could be -1 if there's an error. So I should be error checking, but I'm not. Now let's run it. I'm the parent, I'm the child. Isn't this weird? So what happens? We get two processes when we fork. One of them sees that the return value from fork was 0. The other sees that it was non-zero. The one that sees that the return value was 0 is the child. The one that sees that it was non-zero is the parent. It's not so much that the function executes itself, it's that it's being executed by two processes at the same time. So one way I think about code is that I imagine that there's a little arrow here that's telling me which line is executing. So we execute this line, then we execute that line, then we maybe execute this line, and then we execute this line, and then we're done. But when and that's the way it is at the beginning. Up here, there's just one of these going, just one process. But then as soon as we fork, we've got two of them running. The operating system decides which ones to run next. It can only run so many things at once, so it makes a decision. It's like, oh, I'm going to do process number 1, which is the parent. I'm going to run that next. And the parent gets a non-zero PID. So PID for the parent is non-zero. And so the parent runs here. The child's still up here, hasn't run yet. Parent says, is the PID 0? It's not. So I'm going to run this, and I'm going to print out that I'm the parent. And then I'm going to return 0, and I'm going to be done. And then the operating system later on is like, oh, I got this other one to still run. So number 2, fork returns 0 for you. So we go here and check to see if PID is 0. It is, and we print I'm the child. And then we return and we're done. So, I'll get back to that one. Jonathan, do they run synchronously? They both run at the same time, and that does seem dangerous. But there is one thing that makes it a lot safer, and that is that both processes, even though they're running the same code, they get their own copies of all the local variables. In fact, they get their own copies of all memory. So not just local variables, but anything that was Mallocked, anything else. You can think of the child process as being kind of like a clone of the parent process at that point. If you want to share data between the two processes, you have to go out of your way pretty hard, and we're not even going to talk about that. So the processes, I'm going to do some terminology there with processes and threads. The threads are usually considered to be what like lightweight processes, but really the difference today that I would consider between threads and processes is that threads are just like processes, except they share all their memory, whereas processes do not share all their memory. So threads and processes will both run through the same code, but threads will share all the variables. Processes will not share all the variables. So here we're forking new processes. We don't share any of the variables. They all get their own copies. So because of that, if the parent changes something, the child doesn't see the change. The child has its own copies of all the variables. That's a good question. When executing the fork, it starts, it actually starts on line 8. So when fork returns, it returns to the child process and it returns to the parent process. So that once fork returns, child gets its own copy of PID here, and once fork returns, parent gets its own copy. So fork returns effectively twice, once per process, but there are 2 processes now. So it's not so much, Marshall, that it wants to run twice. It's just that we've started the new process there, and so it's going to run. Like processes just run from one instruction to the next. And so if we create a new one here, it's going to do what processes do, and it's going to go run the next instruction and the next instruction and so on. It's almost like I don't know. Imagine a slope that you can put tennis balls on. You put the tennis ball on the slope and it starts rolling down the hill. If you wait for it to get halfway down the hill and then you put another tennis ball right next to it, they're both going to start rolling down the hill, right? But they'll both start from wherever you put the tennis ball down on the hill. The fork works the same way. The process will just start running from wherever the fork was. When you created the new process, bam, it just starts running code from there. Uh, what am I missing? How come the parent doesn't return to 0? Oh, okay. Maybe this is both related questions here. I'm so confused. Where does the child process get PID value 0? Is it from line 16? How does it go back up to line 11? All right, let's see if this straightens this out. First of all, second question first, it doesn't go back. The child process only does one thing. It gets the return value from fork. It checks to see if it's 0 or not. It is. It prints this out, and then it exits. It's done. The child process dies at that point. So it never goes back. The parent process is still up here, though, potentially, depending on which one gets run first. So we see 2 lines of output, but it's because we have 2 processes there. The child process gets the value of 0 right here on line 8. It's almost as if the code we're running, so we're running our regular single process right here, blah, blah, blah. We get to this line, and the operating system's like, oh, we want to make a new process? Great, let's do that. Bam, bam. There we go. We've done it. And now the parent process runs this line, and then it's the return value from fork is something non-zero, so the parent process comes down here and prints on the parent. Meanwhile, we got this whole other one now. It's like we've made an entire new process. And this is where the child is. The child sees that the PID is 0, it runs this code, prints out it's the child, and then it exits. So nothing goes back. It's just that there are two of them now. Oh boy, I'll bet CTutor won't run it, but we can try. If this runs, I'm gonna freak out. This seems to be exactly the sort of thing that it would. Int. The code may also contain unsupported features. I'll bet you anything that's what it is. I'll bet it doesn't support fork. Having the fork, maybe this will also help Cy. Having the fork in there is very similar to simply running the program twice. We just had a plain old hello world program, and we built that puppy up, and we decided we'd run it twice at once. Whoops. By actually running it. Come on, Beach. There we go. Here I'm making two processes, right? One after another. And it prints it twice. We're doing something similar with the fork, except instead of making new processes at the shell, we're making a new process right here. Let's see, how does the line PID equals fork assign 0? So I can't answer that without talking about like internals. Let's see, fork, new process, return value. It's operating system magic is going to be my hand wavy answer. But since the operating system is responsible for scheduling when processes run, it's responsible for creating processes, it's responsible for destroying processes, this is how it does it. So right here in the man page, it just says like, hey, upon successful completion, fork returns 0 to the child process and returns the process ID of the child process to the parent. So basically when we call fork, which is a system call, we wake up the operating system, and the operating system's like, oh, you want me to do what? You want me to make a new process right here? Okay, I'll do that. So it creates a new process. It has like structures internally where it's like, okay, I'm going to create a process. It's got all the information processes need. And then I'm going to return, I'm going to wake up both of these processes, the parent, because I'm done with fork, and the child, because it's done with fork. I'll wake them both up and say like, oh, hey, child process, you're awake. Your return value from fork is 0. Congratulations. Parent process, you're awake. Your return value from fork is the process ID of that child that you just made. Go for it. But deep inside the operating system, that happens. Yikes, it's 9 minutes after. I've totally gone over and I didn't even realize. Anyway, this was fork introduction. There are a lot of system calls. In the GitHub repo that I'm going to send out to you today, fork is a big part of it, but then there's some other ones, exec and wait, show up. Keep the questions coming about these things because, again, conceptually, fork is weird, right? I mean, you do a thing, you get 2 copies of each process, and they're both running. You get different return values from the same function. Weird stuff to wrap your head around. Yeah, it's on Friday. So ask a lot of questions. Like, we expect in this C week that there are going to be tons of questions about tons of things. So lay them on. Don't forget to go into your PM group channels, ask them there, ask them in the help channel. Yeah, end of Thursday. But for this next bit, we'll mess around with the OS and kind of see what kind of stuff we can do. We can create processes and destroy them and so on. And certainly questions about concepts, bring those up early and often. And I apologize for going over. I'll let everybody run off now, and I'll post the video as soon as I can. And I'll post the GitHub link also immediately. Any last questions? I could talk about Unix system programming forever. It's my favorite topic, so. I'll see if I can find you a list. All right, gang. Have good time hacking and keep the questions coming. All right, catch y'all soon.